The last property of transition metals is that their complexes tend to be very colorful. So in order to figure out and understand why that is, we first have to quickly review about color. What makes things have color? Well, it usually has to do with their electrons, but unlike the electron emission spectra that we saw with hydrogen back in the atomic structure unit, where we talked about electrons dropping down energy levels, and that creates the emission of a very particular wavelength of light, most things that are colored are actually colored because when white light hits them, certain wavelengths of that light, of that white light, which contains all the colors of the rainbow, are absorbed out of the white light, and then the remaining wavelengths, which are reflected or transmitted, those wavelengths are actually what get to our eye. Here's my eye. And when those wavelengths go into your eye, that gets sent to your brain, and that gets interpreted as a certain color. So in this example, all of these wavelengths together, the purple, the blue, the green, and the yellow, in my brain tell me this thing looks blue. And when I see all of these together, my brain tells me that looks white. So in this example, the blue solution is absorbing the sort of orange and red wavelengths of light, of visible light. And so it's the remaining wavelengths of light that create the color. So really important difference here is that when you describe what creates the color, it's not the emission of light. And they're going to look for that misconception. That's what creates the light in the hydrogen emission spectrum. But in this one, what creates the color is actually the absorption of certain wavelengths that we call the complementary color to what we actually observe. So let's go down to see that. The complementary color is the color across from the color you observe in this color wheel. Now the color wheel is very easy to come up with on your own if you know Roy G. Biv. Now we sort of cut out indigo because it's kind of just an in-between blue-violet anyways. And so red and green are complementary colors, yellow and violet or yellow and purple are complementary colors, and orange and blue are complementary colors. So that means if you see something red, it's very likely that it's absorbing green wavelengths of light. If something is appearing orange, it's absorbing blue. If something appears yellow, it's absorbing violet, and so on. So that's usually what's making something have a particular color. The molecules in that substance, something about their electrons are able to absorb this other kind of electromagnetic radiation. They typically absorb over a range. That's what this graph was showing. There's one wavelength in particular that they absorb best, they absorb the most, but there's kind of this whole range of wavelengths that the molecules are able to absorb. And so they absorb different parts of the visible spectrum out of the visible spectrum, out of the white light. The remaining wavelengths that get transmitted and reflected give us the color that we see. And so the ones being absorbed, we don't see. Okay, so now we have to look at transition metals and their complexes and try to figure out why they are doing this. Why are they absorbing visible light, or what part of them is absorbing visible light? If we do electron configurations, and all of these have argon, so zinc starts out like this, but when it's zinc 2+, we get rid of its 4s2. Copper 1+ begins as 4s1 3d10, so when it's 1+, we get 4s1. And Sc3+ is Ar, and then nothing, because scandium would normally be 4s2 3d1, it becomes 3+, and we lose all these ions. So these three ions have no color, the three examples that I began with. So these are not colorful, or no color. I could also just say they're colorless. When I have solutions that contain zinc ions, zinc 2+, copper 1+ ions, or scandium 3+ ions, they have no color. They're completely clear and colorless. And if we look at what they have in common, these two both have a full D sublevel, and this one has an empty d sublevel. Now that's pretty unique because the definition of a transition metal is something that has an incomplete d sublevel in one or more of its oxidation states. So for example, copper 2+ has the configuration Ar3d9. That is an incomplete sublevel, d sublevel, and copper 2, as we know, is a beautiful blue color. Scandium 2+ has the configuration 3d1 that also has an incomplete d sublevel. That ion also has color. So there's something about this incomplete d sublevel that is linked to color, whereas a full level or an empty level will not yield color. Okay, so again, we're getting closer to trying to explain where this could come from. We're going to focus just on octahedral complexes to keep things as simple as possible. Obviously, it changes a bit when we talk about the other shapes, but the only shape that you need to think about is octahedral. So if you think about octahedral ligands, like in this example, iron with these 6 water ligands, then you have a water molecule with a coordinate covalent bond sticking off here, and here, and here, here. You get the idea, and these 6 different directions. Now, what you have to remember is that a coordinate covalent bond is made of 2 electrons. So it's made of negative charge. So we now have like 6 electron domains, if you will, around the central metal atom from the 6 coordinate covalent bonds. That equals 6 electron domains. Okay. But if we think about the metal ion itself, the iron, in this case it's iron 3+. Iron 3+ has a configuration of Ar and then 3d5. So if we were going to draw out the orbital diagram for iron 3+, it has, we would draw it like this, with 1 electron in every orbital. Okay, now we got to connect these 2 ideas. This is the orbital diagram. This is where we would expect the electrons to be in an iron 3+ ion. But now we know that we have these other electrons that have come in from the water molecules and formed bonds. Okay, so bear with me as this gets a little complicated. These are the 5 d orbitals of any atom that has d orbitals. And this is how they are projected to exist based on the mathematical equations. This is where we get the d orbitals. Now, if you can look closely, you'll notice that these 2 on the left, these orbitals are along the axes. This one is along the z-axis, and these 2 are along the y and the x-axes. And that's the same orientation as the ligands. So these ligands we think of as happening right along the z and x and the y. Whereas these 3 on the right are not along the axes. You can see they exist in the spaces between the axes. Okay, so what we get from that is that because of these ligands, because of these electron domains that have formed from the ligands and these coordinate covalent bonds, where we used to have, think of 5 d orbitals that were all the same, we now have actually 2 different levels of d orbitals. So what we're going to see is that the d level, which used to be 5 even orbitals, or when you just have a lone atom, is 5 orbitals of equal energy. In the presence of ligands, they actually split into 2 slightly different energy levels. So this is when ligands are bonded. All of those extra electrons that the ligands have donated in these bonds create extra repulsion with the d orbitals, and it causes the d orbitals to have these different energies. It's now going to be less repulsive for the d electrons to exist in these 3, because if they can do that, they won't be right along the same orientation as the coordinate covalent bonds. Whereas these ones involve more repulsion with the ligands and those bonds that the ligands have formed. So in the presence of ligands, we get the 5 orbitals of the d sublevel actually splitting into 2 slightly different sublevels. And now we have the setup for the absorption of light. Because if we have any space in this top level, and if the right energy light shines on this complex, then an electron from the lower level can absorb energy and move up in energy levels. And that wavelength of light will be absorbed out of the white light, and the remaining wavelengths will pass through. So only energy of a certain type will be absorbed because there's a particular energy difference between these 2 d sublevels that we have. So the key ideas here, to summarize, is that with ligands, the d sublevel splits into 2 sublevels. And I know people don't like that idea, but you're going to have to roll with it. Okay? You had 5 orbitals, and now you still have 5 orbitals, but there's 2 that are higher energy than the other 3. The difference in energy between those 2 little sublevels, so the delta E, the difference in energy, is in the range of visible light. And so now when visible light shines on this complex that has the d orbitals like this, electrons absorb energy and transition up, and the complementary color is observed. So whatever gets absorbed, so if this difference here in this example happens to be green light being absorbed, then all the green wavelengths are being absorbed by these electrons, moving them up to the higher d sublevel. And so when we look at this thing, it's going to look green to us. Sorry, it's going to look red to us because the greens are all being absorbed. So we're going to see red. So the electrons are absorbing certain energies of light, transitioning up to the higher d sublevel, and then we end up seeing the complementary color. So going back to why we don't see color in certain things, if you have something like copper 1+ or zinc ion, zinc 2+, then the d sublevel is full. And if the d sublevel is full, then there's no room for electrons to jump, so you don't get any color. You can also imagine like that scandium 3+. If the d sublevel is empty, there are no electrons to jump up anyways, also colorless. The third situation where you'll get no color is if there are no ligands. So if there aren't any ligands on the ion, then the d sublevel doesn't split, and so you don't get the ability to absorb that visible light. So you need to have ligands, and you need to have the incomplete d sublevel. By having the incomplete d sublevel, you have electrons present in the lower level that can absorb visible light and jump to the higher level. And that absorption creates the appearance of the complementary color. So they love this topic. They ask about it on basically every IB exam. So even though it's complicated, we have to be prepared to explain where the color comes from and to do some predictions about what colors we would see.